Welcome to AI Tuber Podcasts. This is the YouTube series where we really dig into the latest AI and tech research papers.
That's right. And today we're looking at a really interesting one from Essential AI called Rethinking Reflection in Pre-Training.
Yeah, this one definitely caught my eye. It pushes back on a pretty common idea in the field, doesn't it?
It really does. The usual thinking is that, language models learn to reflect on their own reasoning, spot mistakes, correct themselves mostly during that reinforcement learning stage, like after the main training.
Exactly. So for everyone watching, especially if you just want the quick version for, say, your short-form fix, here's the gist. This paper argues, and shows pretty strong evidence, that this self-correction ability, it actually starts way earlier, right in the pre-training phase.
They came up with this clever way to test it, using examples where the reasoning is deliberately wrong.
Right, to see if the models, even partway through pre-training, can catch those mistakes. And what they found is pretty cool. Even medium-sized models, trained on big data sets, start showing this reflective ability.
And it gets better the more compute you throw at the pre-training.
Yeah, it scales. So it suggests these fundamental reasoning skills, including fixing errors, are getting baked in right from the start.
Which has some big implications for how we build these models.
Totally. So today, we'll unpack how they did this, looking at these sort of adversarial data sets they created, what they observed, and what it all means for us, the researchers and engineers actually working with this tech.
Okay, let's dive in then. The core question, as we said, is when does this reflection ability actually show up in LMs?
Because the standard story has been, pre-training gives the raw knowledge, and then RL fine-tuning teaches the model to think about that knowledge, to reason critically.
Exactly. But the authors here are saying, hold on, maybe that critical thinking muscle starts developing much sooner. They argue we need to look across the whole training process, but they put a real spotlight on pre-training.
But measuring that is tricky, right? How do you benchmark something like reflection reliably?
That's the challenge they highlight: existing data sets. Well, they aren't really built for this. Reflection might not happen often, or it happens in all sorts of different ways, depending on the model and the task. Makes it hard to compare apples to apples.
But they needed a new framework.
Precisely. And they start by making a really useful distinction: situational reflection versus self-reflection.
Okay, break those down for us.
So situational reflection is when the model looks at reasoning from an outside source. Think of it like reviewing someone else's code or logic. Can it spot the bug in that?
Got it. And self-reflection.
That's the model looking inward, scrutinizing its own steps, its own chain of thought. Can it catch its own mistakes?
Okay, that makes sense. Two different skills, potentially.
Right. And to measure this during pre-training, their main idea was to see how well a model solves a task when you deliberately give it flawed reasoning designed to push it off track.
So if it still gets the right answer, despite the bad hint, it must be doing some kind of reflection.
Basically, yeah. It lets them kind of probe that inherent reflective capability at different points in the pre-training journey.
And they have that example in figure 2, right? The Olmo model.
Yeah, that's a great illustration. It's an Olmo 2 model, partially trained, working on a coding problem. First, it gets it wrong.
Okay.
Then they feed its own flawed reasoning back to it, but just add the word wait.
Just wait. That's it.
Yep. And suddenly the model goes, catches its error and outputs the correct code. You see the whole process. Wrong answer, pause, correction. It's pretty compelling evidence of that early self-correction kicking in.
Wow. So how did they scale that idea up? They couldn't just manually check everything.
No, definitely not. They developed a way to create these adversarial reflection datasets automatically or programmatically, as they put it. The key was injecting errors into chains of thought, those step-by-step reasoning paths models use.
And by programmatically, you mean they could control the kinds of errors?
Exactly. They could control the type of error, how subtle it was, which means they could control how much reflection was needed to overcome it. It gives them a really fine-grained tool.
Plus, sticking to that chain of thought format means they could adapt existing benchmarks, which is efficient.
Super efficient. Fast, cheap way to generate lots of diverse test cases specifically designed to trigger and measure reflection.
And what kinds of tasks did these new data sets cover?
A good range. 6 new data sets covering math, coding, logical reasoning, and even knowledge acquisition. And crucially, designed to test both situational and self-reflection.
Okay, so they've got the setup. Now, how do they actually define and quantify reflection? You mentioned two types earlier.
Right, explicit and implicit reflection. Explicit is when the model actually says something like, wait, that's wrong, or hold on, the calculation there is incorrect. It outputs specific words or phrases acknowledging the mistake in the reasoning it was given.
So it's verbalizing the error spotting. Does it have to get the final answer right for it to count as explicit?
Not necessarily, and that's an important point the paper makes. The model might spot a flaw and say so, but still fumble the final answer. It's the acknowledgement that makes it explicit reflection.
Okay.
And they give some fun examples in Table 5, like a model working on a math problem saying, wait, 42.6 is not a whole number. Or another one, maybe on a logic puzzle, outputting, wait, we forgot the cow. Little flags showing it's engaging critically.
Forgot the cow. Love it. Okay, so that's explicit. What about implicit reflection?
Implicit is trickier. It's when the model gets the correct answer despite the flawed reasoning, but without explicitly pointing out the error.
So it somehow navigated around the bad advice without saying the advice was bad.
Exactly. The key definition here is that for it to be implicit reflection in this study, the final answer must be correct. If the answer's right and there's no explicit correction flagged, they attribute that success to implicit reflection.
Like it just knew better, maybe. Overrode the flawed input silently.
Sort of, yeah. Now, measuring this automatically. For explicit reflection, they used another LLM, DeepSeek v3, trained as a classifier. They prompted it to read the model's output and decide if it contained explicit error correction language.
How reliable was that classifier?
They checked it against human judgments, as you'd hope. Table 4 shows the details. There's a bit of a trade-off. Precision versus recall. It might miss some subtle cases, but they tuned it to be pretty confident when it did flag something as explicit reflection. High precision.
Okay, makes sense. And measuring implicit.
That was more straightforward based on their definition. If the model got the right answer on an adversarial problem and the explicit reflection classifier didn't fire, then bingo, they counted it as implicit reflection.
Gotcha. And they had specific metrics for all this, right? In Table 3.
Yep. Things like overall accuracy, the explicit reflection rate, how often it explicitly reflected, implicit accuracy, accuracy achieved implicitly, and explicit accuracy, accuracy achieved explicitly. Gives a pretty full picture.
Okay, so that's the setup and the measurement. What about the actual experiments? What models did they test?
They looked at partially pre-trained models, specifically varying the compute budget, so different parameter counts and different amounts of training data seen.
And they ran both the situational and self-reflection tasks we talked about?
Correct. Looking closely at whether the outputs showed that explicit reflective reasoning. The main model family was ULMO 2, the 7 billion, 13 billion, and 32 billion parameter versions.
But they looked beyond ULMO 2.
You did. They also included Quinn 2.5 models, which gave them a much wider range of scales, from a tiny 0.5 billion parameters up to a hefty 72 billion.
And the data sets were based on standard benchmarks.
Yeah, derived from things like Big Bench Hard, Cruxevil for coding, GSM-8K for math, Trivia QA, the usual suspects. Tables 1 and 2 give the full list, and what's interesting is how they generated the flawed reasoning for these often using powerful models like DeepSeek v3 or GPT-4 to create the initial, subtly incorrect chains of thought.
Using AI to create tests for AI reflection. Okay, so the moment of truth, what do they find?
This is where it gets really interesting, the big takeaway. Reflection isn't just some add-on from fine-tuning. It genuinely seems to emerge during pre-training, and it gets stronger the more pre-training compute you invest.
So let's break that down. What about that explicit situational reflection reviewing someone else's logic?
They found that was actually pretty common. Across almost all the ULMO checkpoints and tasks they looked at, models were explicitly pointing out errors in the given reasoning. There was one exception, a specific coding subtask, but generally, it was prevalent.
And did it correlate with the amount of training?
Strongly. They found a significant positive Pearson correlation, that's a statistical measure for our technical listeners, between accuracy on these tasks and the log of the pre-training compute. Same strong positive correlation for the rate of explicit reflection and the accuracy when reflecting explicitly.
So more pre-training equals better accuracy and more explicit reflection.
Exactly. The better the model gets overall, the more it seems to rely on explicitly identifying and fixing flaws.
And what about implicit reflection in this context?
That showed a low correlation with pre-training compute. It suggests that as models get more training, They shift away from just silently correcting and towards actually articulating the correction.
That's fascinating. Like they're learning to show their work more.
Kind of, yeah. Figure 3 shows this really clearly for the GSM-8K Platinum Math dataset. Most of the accuracy gains you see with more pre-training come from improvements in explicit reflection.
You mentioned an exception, though, Trivia QA.
Right. On Trivia QA, implicit reflection seemed to play a bigger part even with more pre-training. Their guess is that because Trivia QA is very knowledge-based, sometimes the model can just pull the right fact from its memory and override the bad reasoning implicitly, without needing to spell out why the reasoning was wrong.
Interesting nuance. What about those triggers you mentioned earlier, like, wait?
Yeah, that was another cool finding. Models can reflect without any trigger, but adding something simple like wait actually boosted both the rate of explicit reflection and the overall accuracy.
So the trigger helps, but isn't strictly necessary.
Seems that way.
Yeah.
And Figure 4 compares different scenarios. No trigger, a very explicit trigger like, wait, I made a mistake, and just the simple wait.
And the simple wait was effective.
It fell somewhere in the middle performance-wise, but what's really neat is that its effectiveness at prompting explicit reflection increased with more pre-training. The better trained models responded more strongly to that subtle nudge to double-check.
Okay, that covers situational reflection. What about self-reflection, catching their own mistakes?
That, they found, was generally harder and less common.
Which kind of makes sense, right? It's asking the model to critique itself on a problem it already got wrong.
Exactly, it's a tougher bar. But, importantly, they still saw a significant number of cases where models did manage to self-correct.
And did that improve with training too?
Yes. Figure 5 shows this for a coding task. The trend for explicit self-reflection increases with more pre-training, even if actually getting the answer right through self-correction lags a bit initially.
So it suggests maybe the model first learns to recognize its own mistake, and then later gets better at actually fixing it, a developmental order.
That seems to be the implication, yeah. Reflection first, then effective correction.
Now, you mentioned something about compute trade-offs earlier.
Ah, yes, Figure 6. This is really practical. They showed for the big Olmo model, the 32B one, that as they increased the compute spent during pre-training,
Yeah.
the amount of compute needed at test time to reach the same accuracy level on the math problems actually went down.
Wait, so more compute up front during training means less computational effort needed later when you actually use the model.
That's what the data suggests. It implies that building in better reflection during pre-training makes the model more inherently efficient at reasoning later on. It doesn't need as much, say, chain of thought prompting or complex sampling at inference time because the core capability is stronger.
That's a potentially huge finding for efficiency. Was this just an Olmo thing, though?
Good question. They checked with the Quinn 2.5 models, too. Figure 7 shows that, yes, those models also got better on the adversarial tasks as they scaled up in parameter count, which is their proxy for pre-training compute in that case.
Okay, so it looks like a more general trend reflection developing during pre-training isn't specific to one architecture.
Seems that way. And one last piece from the appendix, Appendix E, which I thought was quite insightful. They looked at model perplexity, basically, how surprised a model is by text.
Okay.
Initially, they found models showed a sort of local consistency biases. If they were given flawed reasoning, they actually found the incorrect answer that followed that flawed reasoning to be more plausible, less surprising than the objectively correct answer.
So they prioritize sticking to the flawed logic over being right.
Kind of, yeah. Coherence over correctness, initially. But, and this is the key bit, as pre-training increased, especially in the larger models, that gap in perplexity between the wrong answer following the flaw, and the right answer started to shrink.
Ah, so more training helps them overcome that bias and develop a stronger preference for the actual correct answer, even if the reasoning presented is misleading.
That's exactly what it suggests. A growing internal sense of correctness developing during pre-training.
Wow. Okay, so summing it all up, this paper really makes a strong case that reflection isn't just a post-training add-on. Those seeds are planted much, much earlier.
Right in the pre-training phase. And for people like us working in AI research and engineering, that has some pretty significant implications, wouldn't you say?
Absolutely. I mean, first off, it suggests we should maybe be thinking about pre-training differently. Are there ways to design strategies or data mixes that actually encourage this self-correction ability to develop even better?
That's a great point. And understanding of this early emergence could also change how we approach fine-tuning in RL. If the foundation for reflection is already there, maybe we can build on it more effectively in those later stages to get even more reliable models.
And that compute trade-off finding that really makes you think about resource allocation. Is investing more heavily in pre-training potentially more efficient in the long run than relying on super heavy compute at inference time?
It poses that question very clearly. It's
Right.
about finding the right balance.
Yeah. And the paper kind of leaves us with this provocative thought, doesn't it? If these like germs of reflection are already showing up just from training on broad web data, what can we achieve if we deliberately targeted this? What specific kinds of data or maybe different pre-training goals could we use to really boost this crucial self-reflection skill?
That feels like a huge area for future work. Really exciting possibilities there.
Totally agree. We definitely recommend you check out the full paper. The details on the experiments and analysis are worth reading. We'll drop the link in the description, of course.
Definitely dive in if you can.
And let us know what you think. What are the implications you see from these findings? Jump into the comments below. We'd love to hear your perspective.